Okay, this is just the little tail end of chapter 4 that I didn't, section 4.4 that I didn't quite get slides made for. So these are the ones from the publisher. There are other types of redox reactions, and I just want to go over them really quickly. We've talked about combination reactions. Combination reactions, you've got more than one reactant and they combine to form one product. That's how we recognize those. If we look at this example of nitrogen reacting with hydrogen to form ammonia, just looking at that, you would not necessarily recognize that as an oxidation-reduction reaction. There aren't any ionic compounds, and so it's not real obvious. But if we look at oxidation numbers, we see that oxidation and reduction are occurring. So here we've got nitrogen, and its oxidation number is going to be 0. This is the element. Here we have the element hydrogen. It's going to have an oxidation number of 0. And then over here we have a compound, a molecular compound of nitrogen and hydrogen. And so we've got this competition, and we have to say Fa765. Fluorine, no. Hydrogen, yep. Hydrogen gets what it wants. Hydrogen wants to be +1. There are 3 hydrogens, so a total of +3. And then for this molecule with an overall 0 charge, those oxidation numbers have to add up to 0. So we had +3 from the hydrogens. That means that the other side must be -3. There's only 1 nitrogen in there, and so it's -3. So now, yeah, question?
So even though they both start off as 0, it's still a redox because they're still gaining and losing?
Yes. They're not forming actual ions. It's not a complete transfer like you would have when you form ions, but it's a partial transfer of electrons. And so there is oxidation reduction occurring. And so we can identify what's what by looking at how they change. So the nitrogen is going from 0 to -3. Its oxidation number is being reduced. It's going down, right? It's being reduced. The nitrogen is being reduced. And the hydrogen is going from 0 to +3. Its oxidation number is going up. That's being oxidized. So this is the reduction, and this is the oxidation. Any questions? That's really hard to do without oxidation numbers, because there's no charges. So how do you know what's going on? Decomposition reactions are often, not always, but they can be redox reactions. Here's a couple of examples. Sodium hydride decomposing into sodium and hydrogen. This is an ionic compound. We came across it in an earlier example. The hydrogen has a -1 charge. The sodium has a +1 charge. Those are going to be their oxidation numbers. In the products, we have the element sodium, oxidation number 0. And the element hydrogen, oxidation number 0. So what's being oxidized? Sodium or hydrogen? The hydrogen's being oxidized. It's going from -1 to 0. If we wrote that as a half reaction, going from H plus to H2, there must be 2 of these, and no, sorry, it's not H plus, it's H minus. That's really important, actually. So H minus, then the 2 electrons have to be over here. So this is losing 2 electrons. Losing 2 electrons is oxidation. Oxidation is an increase in oxidation number. Reduction is a reduction in oxidation number. So the sodium going from +1 to 0 is being reduced. Potassium chlorate decomposing into potassium chloride and oxygen. This is an ionic compound. We've got chlorate ion and we've got potassium ion. The potassium is a +1 charge, so it's going to have a +1 oxidation number. The chlorate altogether has a -1 charge. Competition between chlorine and oxygen, Fe765. Fluorine, hydrogen, oxygen. Oxygen gets to be -2. There's 3 of them. So total of -6. So these 2 boxes have to add up to -1 because the charge on the chlorate ion is -1. So that means that the chlorine is +5. And what we see happening over here is that the potassium is still +1. So nothing happened to the potassium. The chlorine went from +5 to -1. Is that oxidation or reduction? Reduction. The oxidation number was reduced. It went down, became more negative. So that's the reduction. And here the oxygen's going from -2 to 0. The oxygen is being oxidized. You can also have what's called a disproportionation reaction. I won't test you on this, but this is kind of interesting. Here we have hydrogen being oxidized and being reduced. So here we have hydrogen peroxide decomposing to form water and oxygen. I'm sorry, it's not the hydrogen, it's the oxygen that's being oxidized and reduced. So in hydrogen peroxide, here's one of the rare examples where oxygen is not 0 or -2. Because we've got hydrogen and oxygen together, Fe765. Fluorine, hydrogen. Hydrogen beats out oxygen. Hydrogen wants to be +1. The oxygen has to be -2. Hydrogen peroxide is not very stable. And this is part of why it's not very stable. Oxygen is not real happy about being -1. He is used to getting his way and being -2 or 0. But this -1 business, not so happy with it. When this decomposes and it makes water, the hydrogen is still +1. But now this oxygen has been reduced to -2. It went from -1 to -2. That's the oxidation number going down. And these oxygens have gone up. They've been oxidized. So some of the oxygen went up, some went down. It's like, we do not like -1. We're happy with 0, we're happy with -2. So you go that way, I'll go this way, but we're getting away from this -1 place. Called disproportionation. Combustion. So this comes back to a question asked earlier about, do all redox reactions involve oxygen? No, they don't, but a lot of them do. And combustion reactions are redox reactions. Here is methane. Methane is the primary component of natural gas. So this is what happens when you light your gas stove. You've got the methane, and it's reacting with oxygen to form carbon dioxide and water. And here we have all of the oxidation numbers identified. So carbon is going from -4 to +4. Carbon's being oxidized. The hydrogen here, +1, hydrogen over there, +1. Nothing happening with the hydrogen. The oxygen is going from 0 to -2 and -2. So it's showing up in 2 different compounds, but it's being reduced in both. So combustion reactions are always oxidation reduction reactions. I'm not sure why that slide is even in